All right, let's talk about graphene. You've almost certainly heard of it, right? This incredible wonder material that's just a single atom thick. But for scientists, the real secret, the real magic, is what the electrons are doing inside of it. For the longest time, they've been on this quest to figure out the rules of the road for these electrons in their tiny quantum world. And well, that quest just took a massive leap forward.
I mean, what if you could actually see them? These forces are like the secret choreography that dictates everything an electron does. But here's the thing, they're unbelievably faint, almost impossible to measure. But just imagine if you could. What kinds of secrets would you find? Well, that's exactly what we're going to dive into.
So to see this invisible dance, you can't just use any old microscope. Scientists had to build something brand new from the ground up. It's called the quantum twisting microscope, or QTM for short. And honestly, it's the hero of our story today. It's a revolutionary piece of tech that's giving us a view of the quantum world like we've never had before.
Okay, so how on earth does this incredible machine actually work? The simplest way to picture it is to think of a record player, but, for atoms. You've got a tip, that's your needle, and a sample, that's your vinyl record. But instead of playing music, this setup maps out the hidden energy landscape of electrons. Let's walk through this. First, they take a super sharp tip that's coated in graphene and bring it incredibly close to another piece of graphene. Then they apply a little bit of voltage. This sets the stage for a bizarre quantum trick called tunneling, where electrons can literally just jump across the gap from the tip to the sample. Now here's the really clever part. They physically twist the sample. This twist changes how the two graphene layers are aligned, which in turn changes the energy and momentum of the electrons. By measuring the flow of those jumping electrons at every single tiny angle of that twist, the QTM builds this beautiful, complete map of their quantum properties. It's just an incredibly smart way to see what's going on.
And this isn't just some computer drawing or a concept. This is the real deal. This is the machine, home-built in the lab. You can see that whole stack of precision motors that handles the twisting and the positioning. This is the hardware that is literally letting us peek into the quantum realm. So the team gets their shiny new microscope all set up, they start running the experiments, and the data starts rolling in. But pretty much right away, they knew something was weird. They had stumbled onto their first clue, and it was the start of a real scientific mystery. The results they were getting just didn't match up with anything the existing theories about graphene said they should be seeing. It was like the data was telling them a story, but it was in a language nobody had ever heard before.
And this slide just lays out the whole puzzle perfectly. On the left, you've got expectation. That's what every standard model predicted they'd see. This nice, clean, single hourglass shape. Think of that shape as the sweet spot where tons of electrons can easily make that jump. But on the right, that's reality. That's what the QTM actually saw. See it? That clean hourglass is clearly split right down the middle.
Let's zoom in on that split. This wasn't a little glitch or some noise in the machine. This was a clear, repeatable feature that showed up over and over. And that was a huge problem. It meant our basic understanding of how electrons work in graphene was, well, it was missing something big. None of the existing theories could explain this split.
When scientists find a mystery like this, they pretty much become detectives. And the first thing you do in any investigation is rule out the usual suspects. They had to check and double-check all the obvious explanations before they could even think about claiming they'd found something new. Suspect number 1, physical strain. Maybe the graphene was getting stretched or squished in some weird way, and that was messing with the signal. It's a reasonable idea, so they ran a simulation. But nope, as you can see, the model for strain creates a gap at the center, not a split that starts higher up. The signature was all wrong, so strain was officially off the hook.
All right, on to the next suspect. They tried some other, more complicated models of electron behavior, and for a second there, it looked like they had it. The simulation actually predicted a split, but it was the wrong kind of split. It showed up at a totally different energy, and the shape was kind of flipped upside down. So another dead end. It was back to the drawing board.
So, with all the conventional explanations ruled out, the team knew they had to be looking for something deeper. Something that was probably there all along, but was just too faint for older methods to see. They had to look at that secret dance itself.
And the answer turned out to be something called electron-electron interactions. See, electrons aren't just flying around on their own. They all have a negative charge, so they're all constantly, gently pushing and shoving each other. The best analogy is a really crowded dance floor. You can't just move however you want, right? You're always adjusting to the people around you. It's the same for electrons. These little interactions subtly change everyone's energy, and that collective effect was the thing that all the simple models were missing.
And this quote from the research paper says it all. As soon as they plugged in this crowded dance floor effect into their theory, everything just clicked into place. The disagreement wasn't just smaller. It was gone, completely resolved. This was the missing piece of the puzzle.
And here it is. This is the aha moment. On the left, you've got the real-world data from the microscope. On the right, the new theory that includes all that pushing and shoving. I mean, come on, that's not just a good fit, it's a perfect match. The model predicts the split in exactly the right place, with exactly the right shape. That is the smoking gun.
Now for the physics experts watching, here's where it gets really cool. The match was so perfect, the team could actually work backwards and pull a fundamental number out of the data. Graphene's fine structure constant. It's basically a measure of how strong that pushing and shoving is, and they measured it to be about 0.32, which lines up beautifully with what other, much more complicated experiments found at super cool temperatures. It's a huge confirmation.
So, okay, a weird signal gets explained. Why is this such a big deal? Because this discovery is so much bigger than just graphene. What this really is the opening of a brand new window into the quantum world.
So let's just recap the big takeaways here. For the very first time, scientists directly saw these super faint quantum interactions in this particular way. And this is huge, they did it at room temperature. People thought that was impossible because usually heat just scrambles everything. So not only did they verify a fundamental theory, they proved that this quantum twisting microscope is a total game changer for physics.
The secret sauce here is that the QTM's whole method, the twisting, the tunneling, it acts like a quantum amplifier. It takes these tiny whispers, these incredibly subtle effects that are normally impossible to detect, and it cranks up the volume so we can finally see them clearly.
So think about it. We started with a confusing signal, a little puzzle in the data, and we ended up with a fundamental discovery. We can now literally watch the hidden dance of electrons, which leaves us with a really exciting question. Now that we have this powerful new lens on the quantum world, what other secrets are we about to uncover in other materials? The dance is